It's time for Maths with Mr. Thomas.
It certainly is, Grace. Thank you very much. Here we go, chapter 3, lesson number 15. This is the last lesson in the integration chapter. We're looking at integration by parts once again, but now we are applying our knowledge of using integration by parts to some harder examples. Now, examples 1 to 10 are in the first lesson on integration by parts. If you're still unsure of any of that, look back to that first lesson. If you're quite confident with that, then you can now move on to look at some of these harder examples. So we're kicking off, with example 11. Use integration by parts to find the integral of sine to the minus 1 of x dx. Now the first thing we notice is that integration by parts is used when there's the product, but we don't have a product here. We've just got sine to the minus 1 of x. We need something times something, but we don't have that. So we need to first of all have our product. So how could we write this? What could we do? Mary Lou. Perfect. Sine to the minus 1 of x you can write as a product by writing, well, it's going to be the integral of 1 times sine to the minus 1 of x. It's as simple as that. Now we've got a product. It's 1 times sine to the minus 1 of x. So we're needing to differentiate one part, and we're needing to integrate the other part. So which one would you differentiate here? Anybody tell me? Well, you could differentiate one, you would get 0, but that would leave you with integrating sine to the minus 1 of x. And the integral of sine to the minus 1 of x is unknown. That is why we would have to be differentiating sine to the minus 1 of x. So u here would be sine to the minus 1 of x, and v dash, the one that we're integrating, will be 1. So from here you can differentiate sine to the minus 1 of x. Remember from your lesson in differentiation, differentiating inverse trig functions, you will get 1 over the square root of 1 minus x squared. And if you integrate 1 with respect to x, you get, good, you just get 1. Perfect. That means then the integral of sine to the minus 1 of x will be, if you use this formula up here, this is your integration by parts, it is uv minus the integral of u dash v. Remember, the only place you have a dash is in u dash just after the integral. So we'll have u times v will be sine to the minus 1 of x times x. Just put the x first. Then it's take away the integral of, well, it's u dash times v, so it's this times by x. So it'll be the integral of that. What we need to do now is we're needing to integrate this bit. So how could you do that? Excellent, good. Think back to your other method of integration, which is integration by substitution. Because here, if you notice, if you differentiate, forget the negative just now, but if you differentiate x squared, you will get 2x. And you use integration by substitution when one part is linked to another. And if you differentiate x squared, you get 2x. And the x is already another part of this function. So here, you can use integration by substitution, and you would let u equals, what would x become? Perfect, the whole of this part under the square root, because then you'll just have root u under that. So u would equal 1 minus x squared. Over the page then. So we're going to be integrating, this is just from the last page, and u will be 1 minus x squared. We then need to think about the rest of it. So we know we've got a dx, but we're needing a du. And to get that, we take our u and we differentiate it with respect to x. So du by dx will be negative 2x. From there, multiply both sides by dx. And we know then that du equals negative 2x dx. If you think about this, well, we're integrating here, but we've already found out that we're going to swap this with u, so we'll have root u, but we're left with an x dx. So we need to find what x dx is equal to. And here we've got an x dx, but it's being multiplied by negative 2. So divide both sides by negative 2, and therefore we will have negative 1/2 du equals x dx. Brilliant! So we can now swap that. Therefore, the function that we had, if we take this x to the side, it'll give us 1 over the square root of 1 minus x squared times by the x dx. You may wish to think about it this way around. That will therefore become 1 over the square root of u. And this x dx will be negative 1/2 du. We need to go from writing it all in terms of x to writing it all in terms of u. So, from there, well, you've got the square root on the bottom, that's to the power of a half. If you move that to the top, just rewrite this. So you've got this negative a half, just put that front. Move that to the top, so it's u to the negative a half, and we've still got our du. Integrate that then, you know you would add 1 to the power, so negative a half add 1 gives you positive a half. And you would also then divide by that new power. So we're dividing by a half, and dividing by a half is the same as timesing by 2. So you've got this negative a half, that's staying, then you're timesing by the 2, and you've got u to the power of 1/2. After that, a half and 2 will cancel, leaving you with negative u to the power of a half, which will be negative root u. And after that, you know that, well, your substitute is u equals 1 minus x squared, so swap u with 1 minus x squared. So that is what you will get. Notice here there is no need to include the plus c here. You're just going off to the side and working out what this integral will be. When you go back to subbing it into here, then you will have to include your plus c. Although if you do include plus c here, it makes no difference. Therefore, if you integrate sine to the minus 1 of x, just going back to this line up here, well, you've currently got x sine to the minus 1 of x. Take away the integral of all of that, so that's just rewriting that line. And then if you integrate this part here, well, we have just found that you get negative what the square root of 1 minus x squared. Therefore, you will have x sine to the minus 1 of x, take away, and then this part becomes negative 1 square root of 1 minus x squared. And obviously here, you would include your plus c. Perfect, because you are integrating this last part. And after that, well, you've got the two negatives here, so just write that as plus the square root of 1 minus x squared. And that will be your answer. Example 12. Using integration by parts, find the integral of tan to the minus 1 of x. So very similar to example 11. First thing again that you're thinking is that you need a product to use integration by parts. Muzammil, help us all out. What would you do? Brilliant, good. You can rewrite tan to the minus 1 of x as a product, which will be 1 times tan to the minus 1 of x. Well done, Muzammil. After that, you're thinking, right, well, one part I need to differentiate and the other part I need to integrate. Which one would you differentiate? Good, you would differentiate tan to the minus 1 of x, because the integral of tan to the minus 1 of x we don't know. So u is going to be tan to the minus 1 of x, and the one we integrate, the part we integrate, will be 1. Good. If you differentiate tan to the minus 1 of x, think about differentiating inverse trig functions. That will give us 1 over 1 plus x squared. And if we integrate 1 with respect to x, we just get x. Yeah. Therefore, the integral of tan to the minus 1 of x is, use this formula here, so this is your integration by parts, u times v will be tan to the minus 1 of x times x. Just obviously write your x first, so it's not tan to the minus 1 of x times x, because then it might look like x squared, and that would blow your mind. Take away the integral of u dash times v. U dash is this part here, multiply it by v, that is x, so you're taking away the integral of x over 1 plus x squared. Once again, you're thinking, ooh, I need to integrate this. How would you integrate that part? Well, what you can use again is, you got it, integration by substitution. Remember, you use integration by substitution when the derivative of one part is linked to another. And if we differentiate this x squared, we'll get 2x. And you can see x is already part of the function. So the best thing to let u equal, rather than just let it equal x squared, we'll let it equal 1 plus x squared. That will just give you something over u, which makes it a lot easier. So going over the page, we now have to use integration by substitution with u equals 1 plus x squared. This is just from the last page. And you know, when you get that, well, you would then differentiate u. So u equals 1 plus x squared, and differentiate u with respect to x will give us du by dx. So du by dx is 2x. If you multiply both sides by dx, you will end up with du equals 2x dx. Now, if you look back here, this is what we are wanting to integrate. We know, though, we have u equal to 1 plus x squared. So this bottom line here will become u. We need to rewrite all of this in terms of u, so we need to write x dx in terms of u. And if you look here, we have found that 2x dx is equal to du. So how do we get x dx on its own? Divide both sides by 2. Perfect. So a half du will equal x dx. Yeah! From there then, just taking this part that I've put this green part around, the integral of x over 1 plus x squared is equal to, well, again, you may wish to split this up to think about it, that you could take the x to the side, so it was 1 over the 1 plus x squared times your x dx. Either way though, 1 over 1 plus x squared, well, 1 plus x squared is u, so it's going to be the integral of 1 over u. Multiplied by, what is x dx? Good, that's a half du, so we're multiplying by a half du. After that, well, you're thinking, I've got this 1 over u. If I integrate that, it goes to ln u. A half is going to stay as a half, so I'll have a half ln u. And from there, you're thinking, well, I don't want it in terms of u, I want it in terms of x. So you can sub x back in. So we'll have ln and then 1 plus x squared, obviously with that half just staying as it is. What you can even do though, if you think about this, because no matter what value you put in for x, you will always get a positive, you can just put brackets instead of your modulus sign. Because no matter what value you put in for x, you're always going to get a positive number. If you square it and then add 1. Also, again, you're just going off to the side to work this out, so there is no need to include plus c, but you can put it if you want. You're then going to use that back in here, so we're again just taking this line that's dancing about here, look at me, and we're wanting to replace the integral of x over 1 plus x squared with what we found it to be. So we're going to have x tan to the minus 1 of x minus the integral, so it'll be x tan to the minus 1 of x minus, and we worked that out to be a half ln 1 plus x squared, so we can replace this with a half ln x 1 plus x squared plus c, and that is your answer. Example 13, use integration by parts once again to find the integral of x squared cos 3x dx. So again, it's integration by parts. You're thinking to use that when I've got a product. So I'm wanting to differentiate one part and integrate another part. Which part would you differentiate? Which is dead easy to differentiate? Good. If you differentiate x squared, well, that's really simple. You would just get 2x. You would therefore integrate cos 3x. And integrating cos 3x, we know if you integrate cos, it goes to sine. So you'd have sine 3x. But what do you need to remember? Good, divide by the derivative, because it's not just cos x, it's really cos of 3x. You're imagining brackets around that, so divide by the 3, so it's a third sine 3x is what you would get. The integral of that then is going to be, use integration by parts, uv minus the integral of u dash v. Again, the dash is only on the u after the integral sign. So u times v will be x squared times 1/3 sine 3x. Just put the third first of all, then put the x squared, and then put your trig term last. So 1/3 x squared sine 3x. Take away the integral of, and then it's u dash times v. So it's 2x times 1/3 sine 3x. Well, 2 times 1/3 will just be 2/3. I've also got an x, and again, just put the trig term last, the sine 3x. This line here we will come back to later on, and you'll see why a little later. But we are wanting to integrate 2/3 x sine 3x. How would we go about integrating that? What would we be using? Can anybody help me out? Piper, you're a genius. Yes, perfectly right. Well spotted. Because again, we've got a product. We've got the 2/3 x times the sine 3x. We would have to use integration by parts again. Woo! Who is being spoilt? So it is the integral of 2/3 x times sine 3x. So you're using integration by parts. So let's go over the page. We know we're using integration by parts again for this part. So again, we're going to have our u and our v dash. So look for one part that's easy to differentiate. To differentiate, well, it's dead easy to differentiate 2/3 x. Nice and simple, you just get 2/3. Integrating, well, if we integrate the other part, that'll be the sine 3x. And if you integrate that, what would you end up getting? We know if you integrate sine, it goes to negative cos, so you'd have negative cos 3x. But what do you need? Good, divide by the derivative. So you've got negative 1/3 cos 3x. After that, just taking the integral of this part here. Again, you're using integration by parts, so you look at this formula here. Hello! And you are going to have u times v. So u is 2/3 x times negative 1/3 cos 3x, which will give us, well, 2/3 times 1/3, multiply the numerators, multiply the denominators, it will give us 2/9. We've also got this negative, we've got the x as well, and we've got the cos 3x. We are then taking away u dash times v. So u dash times v will be the 2/3 times the negative 1/3, which is negative 2/9. And then you've got the cos 3x. Notice here you're taking away the negative, so you could rewrite that as plus. And then integrating that, well, we've got the negative 2/9 x cos 3x. That is not changing. We've got the 2/9 here. That will stay as it is. And if you integrate cos 3x, well, what will that become? Well, you know if you integrate cos, it goes to sine, so we'll have sine 3x. But what do you need to do? Divide by the derivative. You've got it. So again, you're thinking of cos 3x as cos of, in brackets around the 3x. That will go to sine 3x, as I said, but you're dividing by the 3, which is where that third comes from. After that, well, you're leaving the negative 2/9 x cos 3x as it is, and you're simplifying this part here. 2 times 1, 9 times 3, so you get 2/27 sine 3x. However, that is us just finding the integral of the 2/3 x sine 3x. What we want to do now is we want to go back. If I flick back a page, we can see that the integral of what we were asked for was equal to all of this. And we have now just found this part here. So what we want to do is we want to go back to our question, back to this line, and replace this part with what we just found. So doing that, we will have 1/3 x squared sine 3x take away the integral of 2/3 x sine 3x. That's that line that we just had with the wee star on it. And then the integral here we found out to be negative 2/9 x blah blah blah. So we can replace all that, keep that part as it is, and we're taking away the integral of that part, which is this answer. So we'll have the negative 2/9 x cos 3x plus 2/27 sine 3x. And again, you've got your plus c here on this line. From there, just get rid of these brackets. So we're taking away negative 2/9 and so on, which will make that plus 2/9 x cos 3x. And we're taking away this positive 2/27. So because we're taking that away, we can just write minus 2/27 sine 3x. And your plus c will stay as plus c. Example 14, use integration by parts to find the integral of x sine 2x dx. But this time, look at this. We've got limits. It's between 0 and pi over 2. Once again, for this one, you're thinking, ooh, product. And when it's the product, you use integration by parts. So you look for one part that's easy to differentiate. In this case, it would be x. Perfect. You would differentiate x. And the other part you would integrate. So we're integrating sine 2x. Differentiate x, it goes to 1. It makes this very, very simple then. And if you integrate sine 2x, that would give you, well, you know sine, if you integrate it, you'd get negative cos. So we'll have negative cos 2x. But once again, you're thinking, ooh, well, there's really brackets around that. So you'd have negative cos 2x divided by 2. You divide by the derivative. So you'd have negative 1/2 cos 2x. For that to work it out, because we've got limits, you may be tempted to write down, well, the integral between these limits is going to be, and work that out. But what you're best doing is ignoring the limits for now and just working out the integral itself. Once you've worked out the answer to that, you can then sub the limits in. So ignoring the limits, just say, right, well, the integral without the limits of x sine 2x dx is going to be, and use your integration by parts. So u times v, so I've got negative 1/2, I've got the x, and I've got the cos 2x. Take away the integral of u dash times v. So 1 times this part. So in other words, just this part. After that, you're thinking, ooh, we've got two negatives here, that'll become plus. And then I've got the negative 1/2 x cos 2x, which will stay, and then I can integrate this 1/2 cos 2x. So 1/2 will stay as 1/2. Cos 2x, if you integrate that, you will get sine 2x. But what do you need to do? Good, divide by the derivative. So you'd have a half sine 2x plus c. That's what you would get. From there, just simplify this. So you've got a half times a half, which is going to be a quarter, and the rest will stay as it is. So we have now worked that out. We've worked it out without the limits, which is why we have the plus c. But what we do next is we then go back and we deal with the limits. So we just worked out that from the last page. We worked it out without limits, but now we can deal with them. So when we're dealing with the limits, all we're wanting to do is take our answer and then sub these limits in. So the limits are, we know when we integrate it, that's what we would get. So we'd have that between pi over 2 and 0. So from there, you can replace x with pi over 2, so negative a half times pi over 2, cos times 2 times pi over 2, well, pi over 2 times 2 is going to be pi, plus a quarter times sine of, again, pi over 2 times 2 is just going to be pi. Take away and sub in 0. So negative a half times 0 times cos of 2 times 0, plus a quarter times sine of 2 times 0, which is just 0. After that, if you work that out, well, you've got negative 1 over 2 times pi times cos pi. And you know cos of pi, if you work that out, well, really what you would have here is negative pi over 4. That's where that bit comes from. And cos of pi is going to be negative 1. You're going to have a plus a quarter times sine pi, and sine of pi is just 0. You would then have take away, and that would work out to be, well, because you're multiplying this by 0, you would get 0. And the sine of 0 is also 0, so really this whole bracket just becomes 0. That means your answer then, you would have, well, a quarter times 0, that would disappear, and you're left with negative pi over 4 times negative 1. Two negatives make a positive, and your answer is just pi over 4. Example 15, use integration by parts once again to evaluate the definite integral x e to the power of negative 2x dx between 0 and 1. Once again, it's integration by parts. Use integration by parts if you have a product, which we do here. Yeah! So, you're going to have one part that's easy to differentiate. The easiest part to differentiate would be 1. So we're differentiating 1. Also, if you differentiate that to get 1, then it means you're able to integrate something really easily here. So differentiate u, and that will just give you 1. So u dash is 1. The part we're integrating then will be e to the power of negative 2x. And if we integrate e to the power of anything, it stays as e to the power of whatever that is. However, what do we do when we integrate? You divide by the derivative of the index. Good. So you would then divide that by negative 2. Just moving that to the front, and I would be multiplying by negative 1/2. After that, again, we've got limits here, but when we have limits, it's best to ignore the limits for now and just work out what the integral would be without the limits. So the integral of that, using integration by parts, using this formula, is u times v, so it's x times negative 1/2 e to the negative 2x. So you can write that down, just put in the negative 1/2, then the x, then the e to the minus 2x. I'm taking away the integral of u dash times v, and because I'm just multiplying v by 1, it would just stay as negative 1/2 e to the negative 2x dx. Once again, you're looking at this and you're thinking, ooh, two negatives, what does that make? You got it. And then from there, you can integrate. So the first part will stay as negative 1/2 e to the power of negative 2x plus. 1/2 will stay as 1/2. Again, we're integrating e to the negative 2x, but we know if we integrate e to the power of negative 2x, we just did it here, then you would get e to the power of negative 2x, but you divide by negative 2. So you would have negative 1/2 e to the negative 2x, and in the end you would have plus c. Perfect, because we're ignoring the limits just now, so we've got plus c. After that, well, you can simplify this bit here. We're adding on 1/2 times the negative, so really we're going to be taking away, and then 1/2 times 1/2 will be a quarter, and the rest will stay as it is. After that, well, we've worked out the answer, but without the limits. Now what we need to do is deal with the limits between 0 and 1. So thinking about these limits then, what would we do? Well, we found out that when you integrate x e to the negative 2x, you got this answer up here. So we can say that that will be that answer between the limits 1 and 0. Obviously, we're not putting in that plus c. After that, you would then sub in the 1 in place of x. So it's negative 1/2 times 1 e to the power of negative 2 times 1, which gives you the 2. Take away a quarter e to the power of negative 2 times 1. Take away negative a half times 0 times e to the power of 0, because negative 2 times 0 is 0. Take away a quarter e to the power of, again, negative 2 times 0. Once you do that, well, you've got negative a half times 1, which will be negative a half, and you've got your e to the power of negative 2. You're taking away a quarter e to the power of negative 2. And then you're taking away, and in here, well, this first part, because you're multiplying by 0, will just be 0. And then you're taking away a quarter e to the power of 0. What's anything to the power of 0? 1! Perfect. So it's just going to be 1 quarter. After that, well, you can think I've got negative a half e to the negative 2, and I'm taking away another quarter e to the negative 2. So if we've got negative a half, take away a quarter, well, that would be negative 3/4 e to the negative 2. And I've still got this take away negative a quarter, which will become plus 1 quarter. And after that, well, because you've got 3/4 here and 1 quarter here, you could take out a quarter as a common factor. And if you do that, well, you would have negative 3e to the negative 2 plus 1. But to save putting the negative first, I'll just put the 1 first and swap that around. So I've got the 1 and the negative 3e to the negative 2. And that is your final answer. Last example with integration by parts. Use integration by parts to find the integral of e to the power of x cos x dx. Once again, you use integration by parts when you have a product. Perfect, when you have a product. So here, you want to look for one part that's easy to differentiate and one that's easy to integrate. Well, here, I suppose e to the x is easy to differentiate. So is cos. It doesn't really matter which one we're using. Let's go with e to the power of x, because that's dead easy when you differentiate it. You just get e to the x. Good. If you integrate then, you're going to be integrating cos x. And if you integrate cos x, you get, good, you get sin x. Perfect. What we want to do now then is to integrate that. We would have u times v, e to the power of x times sin x, minus the integral of u dash times v. So the integral of e to the power of x times sin x. What I'm going to do this time though is I'm going to put I equals, so the integral equals. And you'll see why a little later. Because the integral of e to the power of x cos x dx equals, as I said, u times v, so e to the power of x times sin x, take away the integral of u dash times v. So that is what you would get. And this line again, we will come back to it. You'll see why in a little bit. Okay, again, the reason that I'm putting I, you will see that as well. So the integral is just that we're starting with. So we're wanting to integrate e to the power of x sin x with respect to x. How would you do that? What would you do? Max, help us out. Yeah, once again, you're having to use integration by parts. Max, what a guy. Well spotted. So for this, we have to use integration by parts again to find the integral of this part. Because again, it's going to be a product. So once again, you are thinking, I'm having to write down u and work out u dash, v dash, and integrate to get v. So look for one part that's easy to differentiate. Well, you could differentiate e to the power of x easily enough. We just did it. We got e to the power of x. We could integrate sin x easily enough. We know that it's just negative cos x. Once you've done that, well, the integral of, and we're just taking for now the integral of this part. So we can work that out, and that will be, well, you've got u times v minus the integral of u dash v. So u times v will be negative, we're just putting the negative to the front, then the e to the power of x, then our cos x. Then we're taking away the integral of, and we've got u dash times v. So negative, again, e to the power of x times cos x. From there, well, you're taking away the negative, so that will just become a plus. So we've got negative e to the power of x cos x plus the integral of e to the power of x cos x. Now, there is something that you may notice here. Does anybody spot it? Abby, what is it? Perfect, yes. This part here that we have, let me just highlight it. This part here that we're having to integrate is what we have for the question. We're saying to use integration by parts to find the integral of e to the power of x cos x. And we've managed to get around to finding out the integral of e to the power of x cos x. So we're really back to where we started. So for this, the reason that I wrote I, and I is the integral of e to the power of x cos x is because for this example, I can then replace that with I. So I've got negative e to the power of x cos x plus, and then this whole thing that we're integrating, our integral, I'm calling I, so I'm replacing that just with I. And what we then do is we go back up to this line here. So we go back up to this part and we replace this bit that's got the purple around it. We replace that with our answer. So we found the answer to that was negative e to the x cos x plus I. So we can sub that back in here. So going over the page to do that, those are the bits just from the other page that we found. This was the first part. The integral is this bit here. We then split it up and we found what this was. We worked that out and that's what we got. And now we're wanting to sub them back in. So we can say then that the integral is e to the power of x sine x. Take away the integral of e to the power of x sine x dx. That's just this part up here. That's what we started with. But we worked out this part here. We worked out the integral. So that would become e to the power of x sine x. Take away, and then this part here worked out to be this part just there. So that is going to be negative e to the power of x cos x plus I. And then again, you've got your plus c because you're integrating here. After that, we can think about getting rid of these brackets. So you have e to the power of x sine x plus e to the power of x cos x, take away I. And your plus c will just stay as plus c. What we need to do next, though, is we need to think, right, well, the integral that we started with is equal to e to the power of x times sine x plus e to the power of x times cos x minus the integral plus c. So what you need to do is you need to take your i's over to one side. So if you add I to both sides, you will end up with 2i equals, and we've still got e to the power of sine x plus e to the power of x cos x. And if you take out e to the x as a common factor, you'd have e to the power of x times sine x plus cos x. But we weren't asked for the integral of, we weren't asked for 2 times the integral, we're just asked for the integral. So to get that, well, we then need to divide by 2. So the integral will equal half of e to the power of x times sine x plus cos x plus, and what would c become if you divide by 2? Well, a constant, if you divide it by 2, will still be a constant. So you would leave that as plus c. And that would be your answer. This last example is really a never-ending loop that you're getting into, because if you differentiate e to the x, you keep getting e to the x. If you're integrating cos, well, you're just going between sine and cos, sine and cos, sine and cos, sine and cos. So it's never getting to a real answer. You're just getting down to this. So your integral would be that, and that is your final answer. Try these questions. That is 16 examples of using integration by parts if you put that together with lesson 1. Try these harder examples in the booklet on page 77. If you have any problems, let me know. And if you're really struggling with this lesson, you may wish to go back to integration by parts 1 and make sure you're 100% okay before attempting these harder questions. If you are managing these, well done. Brilliant. High five. Awesome.